Which of the following must be true?
Yeah.
Correct. Yeah. Okay, so now we're going to do what we like to call pretend you're the teacher. I'm going to get one of you to come up to the board and work this problem. Before the holidays, we were talking about related rates. And so I need to have everybody think about these problems and remember how we add the action back into the calculus problem and how we can actually show two rates relating to each other. So let's say, Lauren, you're going to get started. Get up here, get started. We'll tag you out if we need to. And feel free to ask questions if you have any questions.
Okay, so the first thing I see here is it's being pumped at a rate of 4.5 cubic inches per minute. So 4.5 inches cubed per minute. Isn't that a rate? So we can write it as 4.5 inches cubed over a minute. And that, what is inches cubed? As soon as you see cubed, what do you think? Volume. So that's change in volume over change in time. That's your first value. You all inches. Now what we need to do is we need to find a formula that relates these two things, that relates the volume to the radius.
Okay, stop. Pause. Help her out. What formula is she going to use for this? They're blowing up a balloon, filling air with the balloon. What formula is she going to use? Okay, so Lauren, pick somebody to tag you out.
Kindly.
What do we do next?
Okay, we have to find a formula that connects all of this stuff together, which we already said was volume. So what is the volume?
Equals 4/3 pi r cubed. Cube.
Okay, now we have to take the derivative of our volume formula.
Because you have to add action to the equation. Like you have to add the time. You have to ddt it, as we said.
And pi is a constant, and this is your variable, so you do 3 times 4 d or dt because you're finding it in terms of t.
Okay, tag out. Pick a person. Heidi, you're up.
Maybe 4.5 equals 4 pi. 4.5 inches.
We know the change in volume and the radius. So what is ddt2, which is 4.5. Everybody's with me on this?
Yes.
Yes, we started.
So my question is, what about the units? Where are the units? 4.5 what? Just squeeze them in. That's okay, we understand. Okay, so we just added the units in. Connor wants to tag out. Who you want, Connor?
AP.
AP.
Where's your unit?
You bring it over.
What?
You gotta divide, bring it over.
Yeah, if they multiply on this side, in order to get it over, you gotta divide. I'm not sure how to simplify the units really.
They just cancel.
Cancel what you can.
The inches just cancel, but they keep that.
2 of the inches cancel,
Yeah, right.
so it's still 1.
Yes, and it's still inches per minute.
Right here, who remembers, first of all, what is the relevance of d or dt? What does d or dt represent? How fast is the radius changing as time is moving, right? So the point to these problems is to add action into like a stationary situation, which is how to find the volume of a sphere to make it actually move, and talk about how those rates relate to each other. 2 questions. How can I simplify in exact form compared to how can I simplify in approximate form, and what do I need to be careful about? So let's talk about exact form. Exact form. Is it okay to really leave a decimal and a whole number fraction?
No.
So we should actually change this fraction into a better fraction so that it does not have.
Multiply by 2.
need
So,
to.
yeah, let's do that real quick. So if I multiply both by 2, I get 9 over 32 pi, and that's inches per minute. And that is the change in radius over the change in time. And so if I put this in my calculator, I get 0.0895 inches per minute is the change in radius over change in time. Any questions? Okay, so today for my example, my guided practice example for you today, I want to like kind of increase the difficulty on these related rate problems a little bit. And so here I have, and I know it's not the actual amount, but here I have a piece of Play-Doh. Okay, it's actually some ticky-tacky I pulled off the wall, but a piece of Play-Doh. And imagine, and you have to really use your imagination, that you are taking, you have a solid machine with 2 flat plates, and it rolls the Play-Doh, and it rolls the Play-Doh. Okay, so, and we need to talk about all the things that are changing in this Play-Doh. Now, it is Calc 1, right? It can't be too complicated, so it'll be a cylindrical shaped piece of Play-Doh, which means it's going to be perfectly round and perfectly flat on the ends. Everybody with me? Okay, so here's my piece of Play-Doh. I stick it in my little Play-Doh. It's kind of like the fuzzy pumper thing machine. You stick it in your little Play-Doh machine and it starts rolling it. Tell me the things that are changing about this piece of Play-Doh.
Surface area.
Say it, Macy. The length, the height of this piece of this little cylinder, right? So it's getting longer and longer. You agree? What else?
Surface area.
Surface area. Surface area is changing. We're going to talk about that. Whether surface area is relevant to this particular problem, but it definitely is changing the surface area, right? What else is changing? So I'm rolling it. I'm rolling it. It's getting longer. What else is happening? Okay, Connor said it. The radius is getting smaller and smaller, correct? And so I'm rolling it. I'm rolling it. What's not changing? The most important fact about this problem, what is not changing? The volume is not changing. Okay? It's reshaping this particular piece of Play-Doh, but the volume is staying constant. Okay? The volume is staying constant. So, as always with these problems, we need to first come up with a formula that, well, let's take the values that they've given us and assign variables to them, because that's always step 1. So let's kind of go through. I am rolling 6 pi cubic inches of Play-Doh. Okay, so what is that? The volume. Now, somebody, Brooke, you tell me. How do I know if I get confused about what 6 pi cubic inches represents? What is the hint in this? Is it the area? Is it a length? Is it the volume? What's the hint in this problem? It's the length. Help her out. It's the cubic. The fact that it's cubic inches. What unit do we measure in cubes? Volume. So if you're stuck, that we blow an air in the balloon or we're doing whatever, if you were stuck about, you're not sure what value that is, look at the unit, because the unit will give you, be an indicator of what it stands for. So the volume is 6 pi inches cubed, not per anything else. The radius is decreasing at a rate of negative 0.02 inches per second. Assign a variable to that. d or dt is equal to negative 0.02 inches per second. Okay, next question. At what rate is the length changing? Tell me, translate that for me in this problem. What does that mean? Find the HDT. Okay, now that's changing at different rates at different times. So when? Find when 4 is equal to 1.2 inches. So it's a related rate problem, and what I taught you when we were doing some of the other problems is you look at the two rates that they give you and the situation, and you come up with a formula that relates those things together. I want to relate the height and the radius of what type of figure? Of a cylinder. Okay? And more importantly, is it surface area?
No.
No, it involves what? Volume. Okay, so what is the formula for volume of a cylinder?
The area of a circle times its height.
Correct. The area of the circle, the base is a circle. The area of a circle times its height. Okay, we kind of talked about that the other day about how to figure out three-dimensional volume. So we're going to start off with volume is equal to, what's the area of the circle? Pi times the radius squared times the height. Now here's why this problem differs from the other problems. It has 3 variables in it. But are they truly variable? Are all 3 of these, the volume, radius, height, are all 3 of these actually variable? Who's not variable? Volume. Now, let me ask you something, Matthew, or anybody for that matter. Volume, as this situation is going, does it stay the same the whole time?
Yes.
Okay, it's not like we freeze frame the DVD and we stopped it at a certain time. For this one, we know that the volume is constant the whole time. It never changes. That's what allows you to make that substitution from the very, very beginning of this problem. It will never change no matter what I do, from when the problem starts to when the problem ends. So right here, I want you to substitute in the actual volume amount, which is what? 6 pi inches cubed. So right here, for volume, it's 6 pi cubic inches. Okay? That's your formula. Okay, you can make that substitution from the very beginning. Can I simplify this formula? And this is a trick to this particular problem. If before I start taking derivatives, if it can be simplified, I look at this problem and there's something I can divide out that will actually uncomplicate my life a lot. The pi. Everybody see how I have pi on both sides? Make your life easy. Let's divide that out on both sides. 6 is equal to radius squared times height. Now I have a formula that relates the radius and the height. How do I add action to
6
it?
inches cubed, right?
Yeah, I'm going to put the unit back in a little bit when I start substituting it. I'm taking it out because I don't want y'all to be confused with the derivative. Okay, so right here, how am I going to do, okay, so this is the second thing that makes this derivative a little more complicated than the others. How do I actually differentiate this?
It'll be a 0 on one side.
It's going to be a 0 on this side. What's this? Good, Wes. Product rule. Okay, so I'm going to give y'all a few minutes. Everybody work right now on differentiating this. Use product rule. Use implicit differentiation. What am I taking the derivative with respect to? Time. Okay, so I'm going to ddt both sides of this equation. Go. Okay, so we just completed the example of the Play-Doh rolling. So what I want to do now is I'm going to give you, pass out a problem. I want you to work it just as an informal assessment. You're going to work this problem and just hand it to me as you're walking out of the classroom. Got it? Okay guys, y'all have a good day.